All right. Well, welcome to the last lecture of Organic 2. And as I've said in previous lectures, uh, this is the last lecture. I don't know how long it's going to take to do nitriles. Not very long. And then I'm just going to do a really brief, very brief description of alpha substitution and carbonyl condensation, which are basically the same as the reactions we just looked at. So it might only be 5 or 10 minutes of material, and then we're done. And when you're listening to this, you will be in the last preparation for the exam, which is already up on Moodle as I speak. And so again, if you've been listening in on the 11 o'clock sessions or looking at the recordings, you know all the details about the exam. Okay, so let's finish with nitriles. We did all the nomenclature for the different functionalities at the very beginning. And so basically what we want to talk about here with nitriles is first how they're prepared and what reactions they undergo. And if you remember, nitriles don't really fit into that same formula that we talked about. And this green pen's not going to work. Hang on. They don't fit into the same structural formula as we saw for a normal carboxylic acid derivative, where we said we had this acyl group attached to some Y that was a good leaving group. Well, a nitrile doesn't have a carbonyl. You basically have this, whatever your R group is, attached to a CN. But the reason that we talk about it as a carboxylic acid derivative is really twofold. The first is, that it can be made easily from a carboxylic acid, right? And the second is that the reactivity of this carbon is very similar to what you would see if it were a carbonyl. It's electrophilic. Nucleophiles will react with that center, pushing these pi electrons out to the end. So that initial reaction is very similar. It doesn't form a tetrahedral intermediate like in the other carbonyl cases, but the reactivity is very similar. All right? And so when we start talking about nitriles, the first thing to talk about is preparation. And fortunately, again, as we've seen with a lot of these, the preparation of nitriles is not necessarily all new. There's going to be some review. And the first is a review reaction. And it's simply, we know how to make nitriles by SN2 reactions. We actually learned that back in the first semester because a CN minus was one of the nucleophiles that we talked about when we talked about SN2 and SN1 reactions. And so that means simply if you have an alkyl halide, and again, SN2 is the best way of doing it, so it's primary, alkyl halide is going to work the best, the normal rules for SN2, and we can react that with sodium cyanide. Just the simple, I'll put the charges here, it's just basically CN minus with a sodium counterion, and so it would just be nucleophile reacting with the electrophilic side of the alkyl halide, displacing the leaving group, simple SN2 reaction, which would substitute the CN where the halide was. Okay, simple way. And by the way, just to keep up, if you're balancing at home, we have sodium bromide as the other byproduct. And so that reaction we've seen, and it, of course, as I said, has the same restrictions that we would see for an SN2 mechanism. Okay, another reaction that we can use is new, and it'll work on a primary amide. And so again, we're using a carboxylic acid derivative functionality and transforming it into another. So we can take a primary amide and transform it into a nitrile, and we call that under the conditions of dehydration. And it's simply where we take, and this would be for your flashcard. And I guess when I made these lecture notes, I picked a nice juicy example. Primary amide, and I'm going to react it with thionyl chloride. Okay, and usually the solvent is benzene, but benzene just being the solvent. And sometimes it requires heat, but really the most important thing to look for in the arrow is thionyl chloride, okay, reacting with this primary amide. And the product of that is the formation of the nitrile. Now, because of the size of the board and the beauty of the magic of the digital process, I can erase this because I know you can look back and see this. But what is the product of this? Make sure I get the number of carbons correct. Okay, and so I've converted this to the nitrile. Byproducts that are going to help us when we look at the mechanism here in a minute is we produce SO2 and 2 equivalents of HCl. Okay, now when you're looking at this and going back and forth, rewinding to look at the product versus the starting material, these two, that carbon and that nitrogen, correspond to the carbonyl of the amide and the nitrogen of the amide. Okay? And so when we look at that mechanistically, you will see that. So let's erase all this and look at the mechanism for this reaction. Okay? Mechanism. Okay, so we have our generic primary amide, and then we have SOCl2. And we've seen thionyl chloride used in reactions before, so we know something about what its reactivity is. And basically, when you're looking at these two, if you remember from previous reaction, when did we use thionyl chloride before? Remember, it was when we had an alcohol and we were converting it to the chloride. The reactive species, this is a partial positive, so that sulfur is acting as the electrophile, and so the nucleophile over here is either going to be the nitrogen or the oxygen, or it's better illustrated as the electrons from the nitrogen move in to form a double bond, and when they do this, that pi bond breaks. Electrons move out and react with the sulfur of the thionyl chloride, okay, resulting in, it's a result of this electron push. We have broken the pi bond. We've made a double bond between the nitrogen and the carbonyl carbon. Now, let's pause for a minute and think, why did this happen? Well, remember, this carbon here has a partial positive charge. So electrons want to move towards it. So here it's just the lone pair on nitrogen that moves towards it. Okay, so we've made this pi bond. But when we broke this pi bond, we made a bond between the oxygen and the sulfur. Okay, and so basically what would happen is these electrons would move up once these electrons come in to form this bond. Those electrons from this pi bond move up to the O, and then as we've seen before with nucleophilic acyl substitution type reactions, we reform the carbonyl and we displace one of the chlorines as a leaving group. And so I know that this is our last lecture in Organic 2. We can follow all of these electron pushings because it's very similar to reactions we've seen. And so the result of that is you're going to form this new bond between the oxygen and the sulfur. Okay, you've reformed the carbonyl, and so you're going to have the Cl minus that was the leaving group that's the counter ion here. Okay, and then you have a plus charge on this nitrogen, so what this Cl does is it just removes one of these protons, and I end up with this intermediate. Right? So there's one of my equivalents of HCl. Okay? Now I have another base And when this reaction is going, you're going to be generating a lot of Lewis bases. And so what happens is basic species takes this proton off, moves these electrons in, okay, to form that bond, which then breaks the carbon to oxygen bond. And so now we have this as our leaving group. And in this process, we are forming what? The triple bond between the carbon and the nitrogen. Okay? And so through the magic of digital technology, I'm going to erase this. And I can show the result of that electron push, which is basically then I've formed the triple bond between the C and the N. And I have initially formed a species that generates the SO2 and another HCl. Okay, so in the end, that Cl that came off pulls another proton, so you can see where you have enough of these Lewis base Cls around to pull off the protons to make this reaction proceed. Okay, so those are two ways of making nitriles. They're both, effective ways. As you could imagine, the most common way is going to be through the SN2 reaction because you have a little more flexibility there. Okay? So now what are the reactions that a nitrile can undergo? Now again, we talked a little bit about this at the beginning of the lecture, and that is the reactivity is similar but not the same. So I want to emphasize this. When we had a simple carboxylic acid derivative, and we were reacting it with a nucleophile. Remember, we always had the nucleophile reacting at the electrophilic center of the carbonyl, breaking the pi bond, moving the electrons out to the oxygen, creating the tetrahedral intermediate. Where we've moved our electrons out to the oxygen, we have the R group that is attached, we have a Y, and then we have the nucleophile. And then we move on from there to products. Now, if you were looking at this in the context of a ketone or aldehyde, that Y would just change to R and H. So with a carbonyl type compound, nucleophile always reacts at that carbonyl compound, giving us this tetrahedral intermediate. We saw that with nucleophilic acyl addition. We saw it with nucleophilic acyl substitution. Okay, but now with nitriles, the situation is a little different, but very similar. Here we have a nucleophile that's going to react. Again, it reacts at that electrophilic carbon, and when it does, it breaks the pi bond and moves the electrons out to nitrogen. But the difference is that doesn't form a tetrahedral intermediate that leads on to products. What does that form? That forms a situation where you have a nucleophile that is added to that carbon of the nitrile, and so that means you then have still a double bond to the nitrogen, but you have the minus charge. So you can see it's kind of similar, but it's not the same because this is an sp3 hybridized carbon and tetrahedral. This is sp2. Okay? But the initial step is occurring in the same way. The intermediate just has a little different geometry. All right? So the first reaction of nitriles that we want to talk about is hydrolysis. Okay, so reaction of this nitrile with water. And before I even start, if you're taking a nitrile and you're going to hydrolyze it, okay, what is going to be the result? And so generic nitrile, knowing what we know about carboxylic acid derivatives. Okay, so I'm taking my nitrile, reacting it with aqueous acid in this case. That hydrolysis should give the carboxylic acid, and it does. And it gives ammonia as the byproduct. Because remember, when we hydrolyze carboxylic acid derivatives, we always get the carboxylic acid. So it's like the reverse reaction of their formation. You always hydrolyze back to the acid. And with a nitrile, it's no different. Okay? Now, you can also do this hydrolysis with a base. Okay, so instead of aqueous acid, aqueous base. And the result of that is going to be the same, okay, where you actually form the acid plus ammonia, which can also be written where you have the carboxylate. We've seen that before because it's under basic conditions, but this is good enough to know. Okay, and so what is the mechanism of this? Okay, so let's do it. Here is your generic nitrile, just using an R group, and I'm going to react it with aqueous base. Okay, and this is going to be the nucleophile reacting with the electrophilic carbon of the nitrile, which breaks this pi bond, moves the electrons out to nitrogen. So that means that intermediate we form, remember, is not a tetrahedral intermediate, but it is the intermediate where I have actually moved, in this case, right, I'm adding this as a neutral nucleophile. And so I'll do it like this, and then my nitrogen, the electrons have moved out to it, so it's got a minus charge. Okay? It's in an aqueous environment. So what will happen is that I will pick up a proton from water. Okay? So I'll put my water here. Pick up a proton from water to alleviate that minus charge, which gives me back an OH minus. All right? That OH minus then is able to react. But first you notice the situation here. We form this intermediate, and let me fix that H. We have this intermediate here, and does it remind you of something structurally we looked at before when we were dealing with triple bonds? I basically reacted this with water now, right? I had this pi bond in the triple bond, and I've added water across it, HO, H2O. So I've added water across that pi bond is essentially what I've done at this point. Well, notice that it formed the OH, and then there's a double bond here. When this was a carbon, we talked about the fact that that was the enol keto. Different forms, this was the enol. Remember, it tautomerized to the keto form. Well, this does the same thing. It tautomerizes. And when it tautomerizes, remember what happens is we basically move this pi bond, so it's between the carbon and the oxygen, and then this H goes to the nitrogen. And so I end up forming this. Okay? So I've essentially initially formed an amide. And then once that forms, we've seen this reaction before. So it's reacting with, you still have your aqueous base. It reacts with this carbonyl carbon, breaks the pi bond, moves the electrons out to oxygen, right? Which comes back in, reforms the carbonyl and spits off the NH2, which then picks up a proton and becomes NH3. So I formed that. This part of the mechanism we've already talked about. If you look back at the chemistry of amides, you'll see that that's basically what happens. Now, it can be possible, as you noticed when we went through that, if you use mildly basic conditions and use the right equivalencies, it is possible to stop at the amide, but that's not really a reaction that we're going to learn. Okay. So hydrolysis of nitriles gives you carboxylic acids. Okay, the next reaction we want to talk about is reduction. And we've done reductions before. Remember, we symbolize it H in brackets. It basically means the nucleophile that we're using in the reaction is a hydride. Okay, and since it's a carboxylic acid derivative, okay, you would imagine that the hydride reagent we should use is lithium aluminum hydride, because sodium borohydride does not work with carboxylic acid derivatives. So yes, that is in fact what we use. So LAH followed by an aqueous acid workup. But in this case, actually neutral water works too. But that's just a subtle point. And so what do you think is going to be the product if I take and by the way, this could be your flashcard reaction. What do you think is going to be the product if I do a reduction on a nitrile? I mean, we know that with carboxylic acid derivatives, we're always adding 2 equivalents of the hydride reagent. We've seen that now, for 2 different exams. And so I know I'm going to add 2 equivalents of hydride to this. So what do you think the product is going to be? The product is basically going to be where I have completely reduced this from the nitrile to the primary amine. Okay, and let me put my methyl on there. So nitrile to primary amine. Notice, this is this carbon, nitrogen. Okay, and so mechanistically, uninteresting. All you have to do is go through the same process where you take your H minus, react it with the nitrile twice, and you'll see that it leads to that product. All right, next reaction we can have on nitriles is again something that I don't think have touched on yet, and that is organometallics. And so this is like your Grignard reagent. And so if we have our generic nitrile, we can react it with a Grignard reagent. Grignard reagent is the equivalent, remember, of just a carbon nucleophile. So your R group is going to react with the electrophilic side of the nitrile, breaking the pi bond, moving the electrons out. Okay? And so what do you think the product's going to end up being? Well, let's kind of follow through the mechanism and see if it can help us figure out exactly what's going to form. Because it may not be completely obvious. Okay, so if the R minus attacks the nitrile, remember the initial intermediate that forms is going to have, here's the R group, here is the R. Let me put a prime on this so we can follow that R. So we have the nucleophile that's added to this, and then we've moved electrons out to the nitrogen. So that is the intermediate that we form. Okay? And then that, in the presence of acid, where we're going to protonate that, actually in the end forms the ketone plus NH3. Now, how is that happening? Because you protonate this and you end up with basically an imine. And then imine, in the presence, when you hydrolyze an imine, you form the ketone. So imine hydrolyzes to ketone. And that's something that we've already seen. Okay? And so to give you an example of this for a flashcard, there is your nitrile. You react it with, and let's just use a methyl Grignard. aqueous acid workup. The conversion is to the ketone. Right? That concludes the reactions of nitriles. All right? And so what I want to do right now is just briefly talk a little bit about alpha substitution. And then we'll talk briefly about carbonyl condensation. And I say that what we're going to see is that these are very similar to reactions we've already talked about. All I want to do is give you enough of an overview of it where you kind of understand that these reactions can be done. Okay, so if you ever see like one question on it on an MCAT or something, you'll know the answer. And so let's start with just a simple description of alpha substitution and say that we have this carbonyl. And I'm going to draw it twice because I want to illustrate. We've already looked at the situation that would happen if you had a nucleophile acting as a nucleophile. And that will do a nucleophilic acyl addition on a ketone, where the nucleophile reacts with that carbonyl, and leads to the alcohol. That reaction we've talked about a lot. In alpha substitution, the difference is our nucleophile is not going to act as a nucleophile. It's actually going to act as a base. And when it acts as a base, it pulls a proton off of the alpha position. Remember, that's alpha, beta, gamma. Pulls a proton off of the alpha position. And when it does that, it forms that anion. So different result. This is what happens when the base acts as a nucleophile. This is what happens when the base acts as a base. Okay, now why would this kind of abstraction of a proton even occur? Because this anion can resonate. So it is stabilized. That also means that this has some character where the minus charge is here, and it has some character where the minus charge is there. So if we were actually talking about this in lecture, we talk about the difference between carbon reactions and the oxygen. So like if you're going to alkylate, here it's C alkylation, here it's O alkylation. And there are conditions that control which is favored. But we're looking at the situation where this is favored. Okay? And so basically now that you've formed this, it behaves as a nucleophile. So you can react it with things like Br2. And it does the same kind of nucleophilic stuff that we've learned about a zillion times. So we can, for example, put a bromine on there in the alpha position. Okay? We could also react it with a primary alkyl halide, for example. And we could alkylate it at that position. Okay? So in essence, that is what alpha substitution is. It's that simple. But the main question is, when does it go through this type of reaction, which we've seen a million examples of, and when does it go through this? There have to be different conditions that favor one versus the other. And the simple answer to this is if you want it to undergo alpha substitution, where you have your nucleophile behaving as a base instead of a nucleophile, it needs to be a base that's not very nucleophilic. And that, we've already talked about that with, remember going back to SN2 versus E2? because it's the same thing, nucleophile versus base. And remember, in that case, nucleophiles mainly behaved as nucleophiles and would do SN2 reactions unless they were bulky and strong. So strong, bulky bases did a different reaction. They behaved as bases and led to E2. Okay, and so it's the same thing here. You need a strong, bulky base. And the one that you typically see used is abbreviated LDA, lithium diisopropyl amide, which is basically this. Okay, and I'm putting the minus charge in there, emphasizing that it's going to behave as a base. And so it's so sterically biased that it doesn't react well as a nucleophile. It's much easier for it to pluck a proton off than react as a nucleophile. So if you ever see a carbonyl compound and an LDA base, and then there's like an electrophile underneath it. So let me write an example. So on the arrow, you'd see LDA, and then you'd see some electrophilic species. And therefore, you know that this was going to be alpha substitution. Now, let me stress the fact to you that as you notice, I'm doing this without lecture notes because I'm just trying to give you some overview. You're not going to get tested on this. This is free. This is just so you kind of know that this kind of stuff happens. Okay, it's not going to. You're not going to be tested on it. All right. Now that's alpha substitution. What about condensation reactions, the carbonyl condensations? Okay, in carbonyl condensations, you're basically you're going to have an element of alpha substitution that we just saw, and an element of our normal nucleophilic acyl substitution or addition. Okay, and so basically what happens is you have, and let's just do a simple aldehyde like this. Okay, and you're going to react it with LDA like we just talked about. And when you do that, you deprotonate and you form this nucleophilic species. Okay, well, instead of reacting with an electrophile, this is going to react with another carbonyl compound. And let's say it's going to react with itself. So once you form this, it can react with itself, which you want to do separately, form all of your anion and then react it with this. But in this particular case, we're the same. You can't necessarily control that. But what would happen if this reacted with the carbonyl carbon and broke that pi bond and moved the electrons out to the oxygen? You'd be forming that same kind of tetrahedral intermediate that we talked about in reference to this carbonyl. Right? So that would mean you'd have, or that nucleophile is added. All right? And you form this. And then if you do a normal aqueous acid workup of this, you protonate that oxygen, just like we've seen in the nucleophilic acyl substitution. So what would form? You'd have that alcohol now attached to this aldehyde. Okay? That is a carbonyl condensation. All right? Now, under the proper conditions, this product, which I'm going to redraw, now can you see the parts? this is the nucleophilic aldehyde that we made with LDA. This is the aldehyde that then was reacted with this nucleophile to give the addition product, which is why it's the alcohol. You can see a situation under the right conditions where you expel water and you end up forming the alpha-beta unsaturated carbonyl system. And again, if we were doing this in detail in lecture, we talk about all that stuff. But for right now, I'm just giving you kind of an overview for your enjoyment. All right. And so you can imagine you can change. I did this example with an aldehyde. If you had a ketone, you could also take it and treat it with LDA. And you could form the same anion, which could act as a nucleophile and react with a carbonyl compound. But what's going to be the issue with a ketone? Here I have a symmetric ketone. You can have, often ketones, of course, have different R groups, right? Then you run into the fact that you're going to have mixtures. And so usually when you're doing these condensations, a common one is actually called an aldol condensation because you're using aldehydes because they're regiospecific. They only have an R group on one side, so there's only one anion that can form. Okay, but you can do it with ketones, but you're going to get a mixture unless these are symmetric. Okay, now what would happen if I took this? We saw what would happen if I took this anion and reacted it with an aldehyde, which would be the same result as if it were a ketone. But what if you react it with something like an ester? Where this was then the nucleophile. That nucleophile reacts with the electrophilic side of the carbonyl, breaks the pi bond, moves the electrons up, forming the tetrahedral intermediate. And so I'm going to erase that arrow line that I just did so I can draw. Now I form that tetrahedral intermediate where I have now this nucleophile has added. Okay, but now these electrons can come back in, and this is a leaving group. So instead of doing the nucleophilic acyl addition reaction, now we're doing a substitution. So can you see how this has all the elements of nucleophilic acyl substitution, nucleophilic acyl addition? The only thing that's changed is now I'm using carbonyl compounds as nucleophiles. That's really the only difference. And so what would be the result of this? I'd have that di-keto product. Okay? And so that's just a brief overview. If you want to look up some more about it, there's probably something in your textbook that goes into detail on this. So if you were planning on taking the MCAT, although I don't know how much, I don't think that this is even stressed. If any of y'all are taking the DAT or the MCAT, it seems that SN2, SN1, E2, E1, and the aromatic reactions seem to be the thing that you'll see the most of, that in nomenclature. All right? And so that's all I've got. This is the end of Organic 2. I wish we were all together today so we could, see each other for the last time, but enjoyed having you in class, and good luck on exam 3, and good luck on the final exam, and keep looking at your email, because as I said yesterday in the 11 o'clock session, which actually I should say because this is going to air on Friday, on Wednesday in our 11 o'clock, I talked about the fact that I may try to schedule a couple of synchronous question and answer sessions during finals week. I'll try to do at least one. because I know everybody's schedule is going to be, crazy because of all the different final exams you're taking, and they probably all have windows. And but just remember, I'm always available on email. I mean, I've responded to a lot in the last couple of days about the final paper, so hopefully I've been getting back quickly enough. I think my record's pretty good on that. All right, so I will. I guess the Friday at 11 o'clock is our last, official session, and so I look forward to seeing some of you there. Bye.